A side note before we dive into the new section, I was pretty happy with the exams. If you have questions, feel free to look at the key. You should be able to see both the your current grade on Canvas, which should be accurate. I put everything in there, including participation, all of that fun stuff. So that should be a correct reflection of your grade. And the exam average was an 84. So damn, y'all, nice job. Okay. We did in chapter 6, back in Calc 1, volumes of revolution. And we started with the idea of a cylinder. And I said, oh, if I want to know what volume is inside this cylinder, I take the area of the circle that is the base and multiply it by the height. Then I took an arbitrary shape and I cut it into cylinders. And each of those little slices was like a coin where the thickness was very small. I want to do the same thing. But instead of with volume, let's talk about the surface area. What is the surface area of this cylinder? Excluding the ends. Just the lateral surface. That's how I made this particular cylinder, wasn't it? Okay, so if I have a cylinder with an open top and an open bottom, I cut and unroll, and I get a rectangle. Oh, wait a minute. When we describe a cylinder, we describe it by the radius and the height. So again, I'm going to go back to my rolled up cylinder, and I'm going to say that the circle in question has a radius of r, and a cylinder side has a height of h. How do I find the area of that rectangle? Dom, if it's length times width, how do I get the length? How do I get the width?
You have to do like pi r squared or say multiply.
Hold that thought. Pi r squared gives me what formula for a circle?
Area.
But I don't want area. Huh? I'm sorry, I thought you were raising your hand. I don't want the area of that circle because I'm going to unroll it. The area is going to be gone. What do I want to get that length? Where is this length found here? It's the circumference. What's the formula for the circumference of a circle?
32 pi r.
Aha. But then the height is still the height. So the area is 2 pi RH. Great. Here's a cone. The cone has a circle at the bottom. Again, I'm going to assume it's an open base. So I'm just rolling up a piece of paper to make a cone. Now, problem is that this cone has a bad top, so I need to make some folds here to try and make that a uniform height, but let's run with the assumption for the moment. Paper drinking cup from one of the old water fountain style cones. What happens if I cut and unroll that? Say again? It's a triangle with a rounded side. Well, it's really part of a circle, as a matter of fact. I get L and 2 pi r. Hey, wait a minute. That means I know this angle. By the definition of radian. Oh, I got to go all the way back to the beginning of trig class. Oh, shit. What is that angle in radians? Open your internet-enabled device and look up radian. Tell me the definition of the unit. Yeah?
It says radius is the SI unit of base angles, which are based on the arc length and radius.
The arc length and the radius. The arc length here is the circumference of our circle once we've unrolled it, and the radius is L. So in radians, this angle, theta, is by definition 2 pi r over L. And again, stealing from my trig class, the area of a part of a circle is 1/2 the radius squared times the angle. Well, wait a minute, I know theta. So the L will cancel, the 2 will cancel, and I'll get pi r L. Huh. And that's just the side, not the circle at the bottom. The lateral surface area. Questions? Yes, sir. This? L squared, and then we put this thing in for theta. That's all. Yeah, I'm using the angle calculation, the definition, arc over radius. And then things came flat and turned out real nice because when I cut that cone, I get a triangle with a curved side, which is part of a circle. Because those two sides are the same. They're both length L. Okay. How does this come into play when I start looking at a volume of revolution? Well, when we did volumes of revolution, we took a curve. And we rotated it. Now, for the moment, I'm going to rotate around the x-axis. So I spin this. And that means down here somewhere, I get something that looks like that. It comes out towards you and then goes back in behind the screen. So I get a circle at each end. This one kind of looks like the glass for a hurricane lamp. Turned sideways. Hurricane lantern, oil lamp. Go to a bar, order a hurricane. They'll serve it in one of these glasses. Oh, good, Ricky. Or even if I just took a single curve. Imagine the curve of the square root of x. Right? Let's spin that. What shape do I get? How about this? There's the curve spun around. Oh. What's the area of the surface of that object? I don't know. But I can cut that up and approximate the surface by taking two x values xi minus 1 and xi, and getting a yi minus 1 and a yi for each of those. I can see what happens when we spin those. And when we spin those, we're going to get a little ring. As a matter of fact, there. Xi minus 1 and xi, each of them have a height. And as I spin it around, I generate a ring. If that ring is thin enough, I can think of it as if it were a cylinder. Now I've taken this cylinder out from here and I've laid it down. So now, over there in that little right picture, the x-axis is up and down. The thickness, the height of that cylinder is the difference between the x's. Well, wait a minute, I know it's the xi is bigger, xi minus 1. That's my height. What's the radius of that cylinder? I don't know. How can I get a good guess for the radius of the cylinder?
That's why you can find diameter first.
But the diameter is going to just be twice the radius, right? And it's still going to come from the curve itself, isn't it? And it's going to change depending on where I am. So somehow that's got to involve my actual equation for my function. I'm not sure getting the diameter first is going to help me, but that's not a bad idea in general. My radius on here is one of those, isn't it? That's the radius of the circle we created. That's either the left or the right, isn't it? Or I could take the one in the middle and use the midpoint idea, right? Oh. Well, I could actually use any point between xi minus 1 and xi. Take its y value and call that the radius. I could take any x value in there. And that would be my radius. But it's going to be tipped, isn't it? That's only an approximation. How do I figure out if this is at an angle? What's going on here? That's a straight line, isn't it? That's a little piece of a straight line. I'm trying to find the length of this curvy piece. That's what we did on Thursday. So if I really want to know the width, that's the height of my cylinder to get 2 pi r h. It's not really delta x. It's got to have that tilted part into it. That's my arc length. So what if instead of using this, I use this? What's my expression for arc length? Yes, Leo.
It would be pi times the radius times L.
That's only for the case of that piece of the circle. And that was the area of that piece. I need to go back to Thursday. What did we say Thursday was the arc length formula? What extra piece did we use to get arc length? Now that's here. I used that big ugly square root thing, didn't I? Oh. Then I've taken into account how that side could be at an angle in different places. And now I add all of this stuff up. 2 pi radius height gives me 2 pi f of x and that's what I integrate. That is the surface area. Now, here's where I get to be sneaky. The very last thing I said on Thursday. What did we call this piece on Thursday? We gave it a name. What did we call it? No, this particular piece of it, that braced item. Well, yeah, we called it a hard integral. It turns out to be a very hard integral in a lot of cases. The arc length differential, we gave it the name ds. So another way to think of this is that our radius is a y value. And we're making little cylinders as we go along, so we need to measure their side lengths. And side length comes from this. So quite frequently, I will write this integral like this. And then I just have to remember that ds is that arc length piece. Questions? This is weird, man. Let's consider a sphere of radius 2. But instead of the whole sphere, I want you to cut off the ends. So what I'm doing, this curve would normally go from -2 to 2, but I'm chopping it off. I want you to take this piece and spin it around the x-axis. And then I want to find the area of this surface. Now, kind of hard to see, but my ring has a curved profile. So if you think of this as a circle that we cut a bit off and then spun around, what I could be asking is, what's the area on this ring? So let's see if we can figure this out. There's the piece I'm rotating around the x-axis. And if I want to use that formula we see right at the top of the screen here, I'm going to say that the surface area is going to go from A to B, which we were explicitly given, 2 pi y. Oh, there's my expression for y right there. ds. Well, ds is that thing. What goes inside the parentheses? So compute for me. Give me that derivative. Okay, wait a minute. dy dx is 1/2 4 minus x squared to the negative 1/2. Negative 2x because of the chain rule. Okay, but the -2 and the 1/2, if I cancel those, I'm just left with the x. I'm sorry, with the negative x. This is to a negative power. It should go on the bottom, isn't it? It's a 1/2 power, so it should be a square root. And then the minus and the x can stay on top. From here on down, all of the hard work is algebra. We simplify that ugly sucker right there. Yeah, I agree with you. But let's do that, because it isn't as you think it is. A lot of nice things happen, just like with the arc length integrals. Jack said, these are hard unless they're rigged as hell. So I rigged this one thoroughly. Let's see what happens in the algebra up here. Negative x squared is just x squared. Square a square root. Square root goes away. If I want to do the subtraction inside that square root, I need a common denominator. Oh, I also need to catch myself. Because way back up there, what did I do that's wrong? That's a plus. If I make a sign error, I'm going to F everything up underneath it. So let's fix that. Now that's better. What happens in here? Leah?
You have to get polynomial 4 minus x squared, 4 minus x squared, and 1.
But then I have 4 minus x squared plus another x squared on the top, right?
I can't track it because it's minus x squared plus x squared.
So I just get a 4 up there. Okay. See that brow squinching? Hold on, Leo, talk to me. But I actually think the algebra you're trying to create is almost right. Talk to me. Because the square root of a fraction is the square root of the top and the square root of the bottom. So that becomes 2 over root 4 minus x squared. And yes, the square roots cancel perfectly. Like I said, rigged as hell. Oh. Well, if those square roots cancel, then this is just the integral of... Careful.
4 pi.
Integral of 4 pi. Which gives me 8 pi as a result. Because I get 4 pi x from 1 to negative 1. And that is a 2 inside those parentheses. Oh, that worked out so much better than I wanted. Now, if it hadn't canceled, I'd have a square root 4 minus x squared in the denominator. And all of a sudden, my brain would be going somewhere in there. I probably have an arc sine, because that's our inverse sine formula, a squared minus x squared. I can use my trig substitutions. And that's why we needed all those crazy methods beforehand, because if this is going to turn out to suck, I'm going to let some of those square root integrals go back to trig functions. Questions? So it turns out that when I first saw this problem, I said, what freaking good is this? Where is this useful? And it took me a very long time to find a physically practical answer for you. I had a number of theoretical answers, I had a number of interesting but weird and archaic answers. The place I have found this used the most is in the area rotating a windmill blade. So when I go out there to those big turbines and I watch those blades cut through the air, they're creating that surface of revolution. And if I know how much air is impacted per square meter of blade, I get power efficiency out of that. So this is environmental engineering. My other favorite version of this is small turbines. If you go down to the waterfront in Pittsburgh, there is a vertical turbine on the water's edge. It's probably about 25, 30 feet tall, but instead of having big blades that spin this way, it spins this way. And so the blades are all long, vertical, connected to upper and lower plates, but they're rotating around the y-axis. So what happens if I want to turn my curves around the y-axis instead of the x-axis? Well, let me actually draw a picture and see if I can adjust the math we've been doing to this new situation. Grab your calculators, give me a graph of the cube root of x. Kind of looks like the tangent inverse, except there isn't a horizontal asymptote. That graph keeps growing. Now, I'm only concerned with what's going on between y equals 1 and y equals 2. Wait a minute. If y equals 1, then x is the calculation device is sitting right next to you. You could even use the one on the table. What's 1 to the third? Good. And if 2 is equal to y, then what's x? So this graph goes like this. But we're not spinning it this way, we're spinning it this way, which means over on the left side, I get a mirror image looks like that. Now, I've drawn this very lopsided because otherwise we're going to run off the edge of my paper. So sorry about that. But what I have here looks like the bell of a trumpet, only it's very wide. Maybe a serving platter, narrow center. But now my roles change. When we did our integral previously, with this picture, our thickness, the height, was kind of in x. Now the height is in y. I need to change the roles of x and y here completely. So instead of doing my integral, 2 pi y, the radius is now this way. The radius is an x value. Which means I'm writing everything in terms of the value y. X equals some function of y, instead of y equals some function of x. I'm just switching the two variables. But if I do it here, then I need to do it in the arc length as well, and we did that on Thursday also. And that means I can do the entire integral in y instead of in x. But notice this is an x value, isn't it? And this is our arc length differential. So again, I will sometimes write this 2 pi x. Yes. Because the radius is an x value instead of a y value. I like those other formulas, the short ones, because I can remember those easier. Shorter formulas easy to remember. I just have to remember what ds is eventually. For the moment, we'll put it on our formula sheet. So, two questions. Question 1, what is our function g of y? And second, what's its derivative? How do I take the equation I've got, the curve, and rewrite it? The x equals g of y.
Just be x equals y cubed.
That's exactly what it would be. And that means that g of y is y cubed. So g prime of y is nice and easy. Which means I can set up this integral right from here. What happened here? What's inside the square root? Hey, y to the fourth stuff with a y cubed outside. What do I have sitting in front of me? A u sub. But I'm missing the 36, right? So I'll get a 1 over 36 in the problem. I know how to do that one. Oh, wait a second. I didn't change my limits. I should change my limits. If y equals 1, then u is 1 plus 9 times 1, that's 10. If y equals 2, u is 2 to the 4th is 16. 16 times 9 is 144. Plus 1, 145. And now that's powerful. Yay! The 2 on top cancels the 18 on the bottom, giving me a 9. 9 times 3 is 27. Pi over 27 times 145 to the 3 halves minus 10 to the 3 halves. And that is going to be some disgusting ass number. So I'm perfectly happy to leave it like that or shove it in my calculator and give me a decimal. And I get roughly 199.5. Big surface area there for that particular shape. Questions? So 2 important things I have to decide when I'm looking at my shape. Which way am I rotating so I know whether the x or the y acts as the radius? And do I have everything else in terms of the correct variable? If the x is the radius, everything needs to be in terms of y. If the y is the radius, then everything needs to be in terms of x. And those are the axes we're rotating around. I'm rotating around the x-axis, I want everything in terms of x. I'm rotating around the y-axis, I want everything in terms of y. This particular idea leads to one of the weirdest things in calculus. Let's consider the graph y equals 1 over x from 1 off to infinity. If I rotate that, I get a shape that looks like this. This particular shape is known as Gabriel's horn or Gabriel's trumpet. And if you think of it, it kind of looks like the bell of a trumpet, but it's infinitely long, so only an angel can carry it. I'm rotating this around the x-axis. Let's find the volume. Chapter 6, section 1. If I rotate, I get a disk for a cross section. The volume is the integral from 1 to infinity, pi times 1 over x squared dx. I know how to do integrals with infinity. And I even know that one is going to converge. Why do I know that one converges? Huh? That's exactly right. If the p-value, the power in the denominator, is bigger than 1, it converges. Which means this is going to give me a number. Limit as t goes to infinity, integral from 1 to t, 1 over x squared dx. That's minus 1 over x from 1 to t. Limit t goes to infinity. So I get pi times the limit, t goes to infinity, negative 1 over t minus negative 1 over 1. What's that limit? That's just 1. because 1 over t is going to go to 0. So I end up with pi times 1, which means this shape has a finite volume. This infinitely long shape has a finite volume. If you wanted to pour paint into it, it would take less than 3.5 gallons. It takes pi gallons to fill this sucker up. What's the area of the surface? What goes inside that set of parentheses? It's the derivative, and ln of x is the antiderivative. I want to go the other way. A common and not completely unreasonable mistake to make. So what do I get as the derivative of 1 over x? Wait a minute. There we go. The derivative of 1 over x will be minus 1 over x squared. Oh, I got to square that. So that's going to be one over x to the 4th. Oh, this is nasty looking. Let's do what Leo suggested the previous one. Let's make a common denominator. So that'll make that x to the 4th over x to the 4th, x to the 4th plus 1 all over x to the 4th. I'll use the trick you did. Split the fraction top and bottom. What's square root of x to the 4th?
X squared.
But that's on the bottom. So I get 1 over x and then a 1 over x squared, which makes that 1 over x cubed on the bottom. And now I have a problem. I don't know how to do that integral. I don't. But what I do know is how to compare it to something. If I take away the 1 on top, then I would make something smaller. What's square root of x to the 4th? Leo just said that x squared. X squared over x cubed. Wait a minute, that's just 1 over x. That means that this integral is bigger than 2 pi integral from 1 to infinity, 1 over x dx. What do you know about that integral? No. The integral that was pi was the integral of 1 over x squared. This is the integral of 1 over x. And that's the one that diverges by our p test. We need p to be bigger than 1. That p is equal to 1. That integral in the box blows up to infinity. Hey, wait a minute. Our surface area is bigger than that. Our surface area must also go to infinity. Here's the paradox. This horn holds pi units of liquid. Its surface area is infinite. You can fill it with paint, but you can't paint the outside. This better be owned by an angel. Nobody else could do that sort of crap. insane. Infinity is weird, man. And it's weirder than I thought it would be. This is a classical paradox dating back to the invention of surface area revolution calculations. So this idea is about 200 some odd years old already. And there's a short video that I put up on our Discord about it. If you want, I'll throw it on the Canvas page as well. But I threw it there. I will see you all on Wednesday. Have a wonderful rest of your day. I believe, if I'm not mistaken, yep, we'll do more applications, practical applications on Wednesday.